Welcome back to Physics 142. In this video, I want to do one more example of using Ampere's law, and then I will make a comment about how to sort of generalize this example that will be useful for your homework. So the example that I want to do is I want to think about a wire, all right? And I want to think about a wire that has that's going to be a cylinder, all right? So we'll think about some cylinder wire. All right, so here is my wire. It's a cylinder, all right? It's going to have some magnetic field going around it, all right? Magnetic field going around it, right? And we're going to have current running through it. So let's draw all this in. So I want some current running through this wire. We'll have that be a current I, all right? And let's say that it's uniformly distributed throughout the wire, right? We have my current I uniformly distributed throughout this wire, all right? We'll have magnetic, so that means the magnetic field is going to be wrapping around the wire, right? That field going around this wire, okay? So there's my magnetic field. And rather than having be a thin wire, right, we want to give this wire some size, all right? So I guess I should have indicated that here, but let's give it a radius, all right? And we will give it a radius capital R, all right? So now we have a thick wire, right? If we wanted to view this wire sort of end on, right? End on, here would be our wire, and now it has a radius big R, all right? And actually, I'm going to draw that a little bit bigger because that's going to be useful, sort of the end on view. It will be useful in just a second. So let's draw this a little bit bigger. All right, and here is the radius R. Okay, so we have uniform current uniformly distributed throughout this wire, and we want to know, I want to know the B field both inside and outside of the wire, all right? So I want to know what the magnetic field is in the wire and what the magnetic field is outside the wire, all right? So find B at radii bigger than R, that is outside the wire, and at radii smaller than big R, that's inside the wire, all right? Okay, so let's go ahead and start with outside the wire, all right? R bigger than R. And this, again, is a nice symmetric situation, all right? We have this nice cylindrical symmetry, and so we can use Ampere's law to find the magnetic field. So let's write down what Ampere's law is. So Ampere's law says that we take the integral of B over some path, and that's going to be equal to mu naught times the amount of current that we've enclosed. So to do that, that means that I need to draw a path that I want to walk around, and I'm interested in radii, you know, I'm interested in radii here that are outside of R, right? So I need little r will be the radius of my path. The symmetry of the situation says it has to be a nice circular path, right, around the wire. And I'm going to give it a radius little r that's, you know, any bit of space bigger than r, right? All right, so I draw my path. I think about my path. I think about walking around the path, and so I want to draw a bunch of little dl vectors, right, that represent my walk around the path, right? You know, little dl vectors. And then I also want to draw in my magnetic field. And when we know magnetic fields need to wrap around the wire if the current is coming out of the page, right? Let's indicate that the current, you know, current I is out of the page, all right? Out of the page. It's in here, right? So we have current I in here, and it's coming out of the page. So maybe put a little dot in there to make that clear. It's coming out of the page. And so that means that the magnetic field is going to wrap around. If I put my thumb coming out of the page, it'll wrap around counterclockwise. All right, so I draw in my B fields here would be going up. My B fields here would be going sideways. Here they're going down, etc. Right, there are my B fields, okay? And so now I can go ahead and take this dot product, and if I've chosen this right, I've got B and DL are parallel, right? They're going in the same direction. And so I now have the integral of the magnitude of B times the magnitude of DL times the cosine of 0, that's the angle between them, is mu naught times I enclosed, all right? And that's good because now these are just values, right? They're no longer vectors, and so I can do things about that. The first thing I can do is I can recognize that the magnitude of B, right? Well, B was all different directions, so B is changing all through my loop, but the magnitude of B, that's just constant, right? That's the same everywhere because no matter what direction I look at this wire, it's going to look the same. So since B is constant, the magnitude of B is constant, I can pull it out of my integral. So magnitude of B is constant. All right, and it's really important really to indicate all of these steps, right? Because you need to make sure that all of these steps are true for your given situation. Otherwise, Ampere's law, mathematically, this will break down, right? So you really have to be careful that all these steps are true. But here it is indeed constant, so I can pull it outside the integral. And then we just have the integral of dl, cosine 0, that's 1, is mu naught times I enclosed. And, well, dl, that is the path that I take here, right? And if I have radius little r, and this is a circle, then that circle is circumference 2 pi little r, right? It's the circumference of my path, right, that I care about, because it's for my path, how far I walked. And so now I have, if I solve for b, b is going to be mu naught times the current that I enclose, which is all of it, so that's I, all right, divided by 2 pi r around the wire. All right, so there's my magnetic field around this wire on the outside of the wire, and that's the same result we got for a really thin wire, and that hopefully makes some good sense. All right, but what about inside the wire? All right, that's where things maybe get a little bit more interesting. All right, what if we want little r less than big R? What if we want to go inside the wire? How are we going to do that? Well, we're going to go through the same steps, okay? We're going to go through the same steps here. So again, we'll write down Ampere's law, all right? B dot dl is going to be mu naught times I enclosed. Okay, but now we're going to walk a different path. Now we need to choose a path that is inside the wire, right? At little r less than big R. So now we're choosing a path in here, right? So now my radius little r, right, is inside of big R. So this will tell me, right, and I can make little r any size, right, from the middle all the way out to here, right? So little r is representing any radius inside. So this will be true anywhere inside this wire, all right? But I'm just going to choose sort of a generic path. I'll make it little r here, all right? And now, again, we have to assume something about the B field, all right? But we know that, the B field needs to follow this cross product, right? We still think of it, there's current still coming through the loop here, right? And we know that the B field is going to have to wrap around that current. So it's still reasonable to assume that our B field is wrapping in the same way, all right? If for some reason it reverses inside the wire or something like that, then we'll get a minus sign at the end and that would tell us, all right? But I think it's reasonable to think that it would loop in the same way because the current is still coming out of the page here, all right? So, okay, so I draw in my B vectors. Really I should draw in some extra DL vectors. It's going to work the same as here, right? My DL vectors are again going to be aligned with my B vectors. And so, the steps here are going to be all the same, right? We'll have a cosine of 0, B is going to be constant, and we'll come outside the integral, all right? So again, we'll have B times 2 pi r, all right? This little r, again, now it's less than big R, is mu naught times I enclosed, all right? So we'll go through all the same steps for this loop inside the wire, except now we have a little difficulty because I enclosed is not all of the current, right? All of the current is spread through this whole thing, right? But we're only using some fraction of the current in here. So we need to figure out what fraction of the current are we actually enclosing, right? We can't just plug in I. We only get to use the current that's actually in here, right? We only get to use the current that's actually enclosed in my loop. So how am I going to figure that out? Well, what I'm doing is I'm enclosing sort of a certain fraction of the volume, or you might think of it as a certain fraction of the area here, right? And well, to think about how much of that area I'm enclosing, right, maybe we'll write that down here. Well, the area that I'm enclosing with the little blue loop, and maybe I'll write it in blue, right? The area I'm enclosing with my little blue loop is pi times little r squared, right? That's the area that's getting enclosed. Whereas the area of the entire wire, right? The area of the entire wire here is going to be pi times big R squared, right? That's the area of the entire wire. And what I need is I need the fraction of the area, right? I need the part that's just inside. So that's going to be the fractional area, right? And so if I take the fraction of the area, well, that's if the current is uniformly distributed throughout it, that will also just give me the fraction of the current, right? The fraction of the area that I'm enclosing tells me what fraction of the current I'm getting. Another way you could think about this is that I divided by pi r squared is the current density, right? Current per area. And so if I take the current density and multiply it by however much area I'm enclosing, right? That gives me the total amount of current that's enclosed. So this is I enclosed, right? This tells me what fraction of I am actually enclosing. It's not all of it, it's just some fraction of it, right? So now over here, we can write B times 2 pi r is mu naught, and then we need this fraction, right? This fraction of I, we can't just write I, times pi little r squared divided by pi big R squared times I, all right? Now we go ahead and divide through by 2 pi r, so let's do that. And these pi's are canceling out, so that's good, all right? And what do we get? Well, we get that B inside, all right, B inside is going to be mu naught times I times r, right, because one r is going to cancel, okay, divided by 2 pi big R squared, right? Because the 2's down here, the 2 pi is down here, 2 pi r, one of the r's cancels, all right? So that's what we get, and it looks like we guessed our direction, all right? So, you know, sort of counter clockwise, right, is how sort of the sense of what our magnetic field will be here. All right, and I just wanted to show you that hopefully, if we've done this right, the magnetic field should sort of match right at the boundary here, right? So if we were to try to plot a graph of what this looked like, all right, if we wanted to plot maybe a graph of what is the magnetic field as a function of radius, all right, if we want to get the magnetic field as a function of radius, all right, and maybe we'll have some breaking point r, okay, inside B goes linearly with little r, right? Little r is just our distance from the center, right? You could change that. Big R is the actual size of the wire. You can't change that. That's just a constant, right? So, but as little r gets bigger, B gets bigger. That's a linear relationship, so they'll just go up, all right? And then once we hit this edge, right, then it looks like we have a 1 over r relationship, right? As r gets bigger, B is actually going to get smaller once we get outside the wire. And 1 over r, well, that's like a hyperbola, so hyperbolas look something like this, right? So we have this sort of 1 over r drop off here, and we have the proportional, the linear rise with r here. Ideally, they should meet right at big R, so we can also double check that, right? And if indeed you plug in a big R here for little r, then you'll get, we plug in big R here, that would be mu naught times I over 2 pi r, and one of the factors of r would cancel, right? Which would be the same as if you plugged in big R here. So indeed, all right, which equals mu naught times I guess I could write this as r over r squared and show the cancellation over 2 pi r. And so indeed, they do match up there, and that's good. That makes some good sense. So we assess our answer here, and we say it makes sense here. Matches at r. All right. Now, This was a good example problem. Before you go, I want to comment on one other sort of interesting example, and that is the example of what if instead of having just a wire, right? What other kind of symmetry could you deal with, right? If you could imagine these cylindrical symmetries. I could maybe, put different shells, a wire inside a wire, that kind of thing. So cylindrical symmetry is one of the options, right? But are there any other symmetries where we can use Ampere's law? Current in a sphere, you could, but usually current's going to be along something, right? Along sort of a wire. And so the other thing that we usually think about is we want to think about, well, what if you have sort of a planar symmetry, right? Could you have sort of like a plane of current, maybe here sort of a plane, and you have a bunch of current all coming out of the page towards you, like basically what that would be is a bunch of wires all next to each other, right? If you had a bunch of wires all with current all next to each other, right? That would be sort of a plane. Could you use Ampere's law in this case to figure out what was going on? And I'm going to suggest that the answer to that is yes. And the way I want to think about that is, what sort of Amperian loop would you draw here? Well, we know if you just have one bit of current, right? One bit of current. What happens with that one bit of current, and I'll move this up just a little bit so we can see a little better. Well, with that one bit of current, we know that the magnetic field just wraps around it in a circle, right? So there you go, so magnetic field wraps around. If I had, say 4 wires next to each other, all stuck next to each other, there you go, 4 wires, all right? Well, would that do? It would just sort of stretch out the magnetic field in this direction, and then it would loop around, right? You just get this sort of, be a little more sort of oval shaped. So you could imagine, right, if you stretch this out to be a whole bunch of these, right, going really, really long, right, what that's doing is essentially along this, right, the magnetic field is just going to be stretched to the point that it's just running parallel to those wires, right? And here it's running like this, right? And it's not going to loop around until it gets down to the ends, right? And so if you're trying to draw some sort of Amperian loop here, all right, if we're interested in, some spot, some distance r above the surface here, a good Amperian loop that I might suggest is, well, you want to go along the field line here, right? And you want to go along the field lines here, and then maybe at some point just take a 90-degree turn and cut here, all right? Because we're going for planar symmetry, so you want it to look the same on the top as the bottom, right? That would exploit the symmetry of the problem. And this will actually end up being really useful, all right? Because at the top here, you'll have, if you walk around, imagine drawing your DL vectors here, right? When you walk around here, when you do B dot DL, right? They'll be in the same direction. They'll be parallel, right? So B dot DL will end up being B dl times cosine of 0, which is just 1, right? Versus here, when you cut up, right, well, now you're running perpendicular, all right? So for your dl vectors on this side, when you do B dot dl, you'll get B dl cosine of 90, all right? And that will just end up being 0. All right, so you get 0 contribution from these sides. And so if you have lots of wires next to each other, this is sort of the setup that you want to use. And then you can use sort of this procedure to work through and figure out what the magnetic field actually is. So hopefully that is helpful to you, and these help you get a little bit better understanding of how we use Ampere's law to find magnetic fields.